Okay, we're here about to looking at our experiment here later on in the day. If through the magic of editing I should have put this first, in which case I'm going to say the correct science, what I hope to be the correct science now, and I might have said some things wrong later on in this video. Ignore that, I was half asleep when I did it. On the other hand, if I have failed in the magic of editing, this may in fact be the second part of my video. If it is, or if this is a second video because I don't know how to get these put together, then let me correct some things that I might have gotten wrong earlier. The purpose of this experiment was in order to demonstrate the importance of using diamine to obtain the crosslink final product in a commercial epoxy resin. Epoxy resins are a kind of thermoset resins. At room temperature, they are pretty much a liquid form. In fact, you can still see, oh, why did I touch that? Why did I do that? Why? I don't have gloves on. Pipe it on the test. You can still see here, I've got room temperature here in my garage where some of the hardener spilled out. Oh, why am I doing this? Pay attention, John. It's still relatively liquid. It's flexible. We can move it around if we want to. Most of these resins are pre-polymers that are set up and to apply and conduct the chemical reaction when they are connected to the connecting polymer. In this case, the diamine, the hardener, will connect to the resin and cause the bonding. It's this bonding which allows for the reason why this bonding becomes so strong is because of crosslinking. Effectively, the molecules are in an AB system and they've got crosslinks due to BB reactions. Basically, the chains, the polymer chains will become joined one on top of the other. Let's see if I can do this. By a branch that will extend between them, and that becomes the cross-linking. The reason these are known as thermoset is because the polymer reaction is at room temperature is fine, but then once you get these two products together is when it becomes chemically, it starts hardening. It does it at room temperature, it does it automatically. You don't have to induce any additional heat or anything like that. The bonding polymerization, as I said, is through the diamine and the resin combining together for the cross-linking. You'll note on the epoxy weld that I have purchased, it is a 1-to-1 ratio, which they typically recommend. Because it is a 1-to-1 ratio that they recommend on their packaging, I would assume, and don't know for sure because I'm just not 100% on it, but I would assume that these are stoichiometrically balanced diamine and resin. Okay, using the commercial epoxy resin, we're going to see about what will happen with the structural intake of the epoxy and how that applies when you coat different sorts of resins. We'll see we've got the epoxy with its accompanying resin. I've already got the package here. You'll note that the standard dosage is an equal amount of each, is what they recommend. And this is for multi-surfaces. This is for iron, steel, aluminum, brass, bronze, copper, pewter, and wood. You'll probably do paper too, but it sounds like overkill. We've also got some 8-inch metal plates, metal frame hinges almost, that I'm going to weld together using the epoxy resin. You notice we have A, B, and C columns and our containers. Container A is going to contain 3 parts epoxy, 3 parts resin. It's going to contain equal parts. Container B is going to contain 1 part epoxy, 3 parts resin. And container C will contain 3 parts epoxy, 1 part resin. Right? theory is, at least what I think will happen, is that well, crap. I've got to pierce it. Use a screwdriver. Where's my knife? A will do the best. Notice I'm wearing gloves because I don't want this on my hands. A is going to do the best because it's going to have equal parts of epoxy and resin. Roughly equal parts. Okay. This is why I'm wearing gloves. I can just wipe that up. Because it has equal parts, it's going to, why is it going to do the best is going to be the actual question we want to answer. And the reason why it's actually going to be doing the best is because the resin and the epoxy itself, by combining together, is going to give it the nice chemical reaction that we want and to allow for the proper structure of the polymer to form. Got a nice little glob there. That's really all I want. Nice little gray goop. Now I'm going to take some right here. I really just want to coat it on one of them. I don't want to coat it over the whole thing because I want to try and give myself a chance to break it apart. I am not really all that strong when it comes to chemically welding things together. So you notice it's not perfectly aligned, but it's nice and flat. I'm now gonna bring this into focus. We'll mark this A, and we'll do it over here too. So we're gonna set this aside. Now, for full strength, it recommends waiting for 24 hours. We're not going to do that because I want to see if I can break them apart. I have no use for this. I'm probably going to throw these parts away afterwards. But for simplicity's sake, we'll see if we can break them apart in about 4 or 5 hours. So B, would have helped if I written this down. Well, video documented. I don't know what I said at the beginning, so B, we're going to do 3 parts. Or no, we're doing 1 part this of the hardener, the epoxy hardener. And we're going to do 3 parts of the resin. Now, unfortunately, when doing an experiment like this is not as exacting as you would probably like it. Definitely not as exacting as I would like it, but we're kind of making do and we're eyeballing it. Notice this has a darker complexion than the other one. That one had more of a gray complexion. This has more of the black of the resin. Woo! It smells stinky. Stinky. So now we're going to put this one here. Now, I think this one should still have a decent bond, just not quite as strong. And the reason why, it's still got, for the piece of hardener that we attached, it's got a full complement of the resin to attach to, so it probably got too much. But that's why I don't think it's going to be an ideal seal. But it'll probably do. The resin is going to act as an activator for the hardener. Alright. So that's there. Label this one B. You can already feel that it's moving more fluidly, even though we just barely set it. It's shifting around a lot more than the A1 did. Set that off to the side. Now for column C. So we did 3 parts of resin there. So now we're going to do 3 parts of the hardener for the epoxy and 1 part resin. Now, I'm not exactly showing the instructions, but the instructions do say you want to try and get whatever you can mixed within 5 minutes, because it starts setting after that. So I'm going to take one little. Sorry to put that little extra bit there, but looks like a little bit that would have been 2 parts resin almost. So I'm going to take my little Q-tip. Oh, this is going to have that nice little pink consistency of the hardener. Whew! Stinky. Let's smell the polymerization right there. Stinky polymerization. This is why I've got the garage door open. I really don't want to smell this any more than I have to. All right, and this will be C. That was more solid than B. Maybe I need to recorrect what I thought. C. Now, we're going to let these sit for a few hours. We're going to come back. We're going to see how they compare when I try and break them apart. Good chance I won't be able to break any of them apart. It is I mean, literally we're chemically welding these metal components together. Now, it's not traditional welding, which uses a heat conductor and well, it's pretty much polymerization in traditional welding too, but this is a chemical in usage instead of... Well, damn, now that I think about it, I think traditional welding is chemical too. You know what? I'll figure it out later. This is not using a welding rod or a welding machine or anything like that. That's what I do know. We'll see if I can take them apart at all, see what the consistency looks like, see which one holds up. A was equal parts epoxy and resin. B was 3 parts resin, 1 part epoxy. Ooh, that's not good. And C, ooh, maybe B is going to be the loose one. C is going to be 3 parts of the hardener, 1 part of the resin. And we'll check again later. Now, in the last section of this video, we come to our moment of truth. We have our samples A, B, and C. A was conducted with a 3-3 balance of epoxy and resin. 3 drops or portions of the diamine hardener and 3 portions of the resin. Let's see if I can break it up. Yep, I broke it up. Heck of a balance. Obviously, I did not apply a good enough job there. Well, we can see where probably I should have done it on both sides in hindsight. Oh well. We can see here that it has hardened to a great degree. It hasn't done the 24 hours that it wanted under A. But you can see where the hardening has occurred, and this is from the equal measures of the diamine hardener and the resin. Sample B had 3 parts resin, 1 part diamine. Notice that is still very predominantly, I don't want to touch it because it's got some in there and I'm not wearing gloves. But notice that you can still see that it is fairly liquid where the resin is because it has not interacted it very much with the diamine. It simply has not been able to cross-link properly because there's been an excess of the resin. C was the application of 3 parts of diamine and 1 part resin. Huh. Well, that's stuck on there. We'll go figure. By applying additional components of the diamine and less of the resin, we've given a lot more diamine to go and cross-link with the little bit of resin that was there. Huh. Maybe it's not stoichiometrically balanced then. Or maybe I did this one wrong. That turns into a question. At the very least, this does turn around and show that the diamine, by virtue of the fact that C is sticking together, I'm sure I could pry it apart if I wanted to by using like a screwdriver or something. Oh, that's interesting. The diamine was the main product here. Because this is the one that's sticking, we can see that the diamine becomes absolutely more important in the completion of the cross-linking process. Huh. Kind of surprised this one didn't stick better though. Well, this concludes my experiment. Now I'm sitting here wondering what I could change to amend the experiment if we wanted to. Yeah, results are results. Sometimes things go wrong. This is science. The diamine becomes incredibly important in the cross-linking in the thermoset epoxy resin. Without it, the reacting resin is just not applicable enough. Notice here again, our B component that had more resin is still very wet. I don't want to touch it, but I'll get some paper there. Well, that's not really doing much, but it's sticking there to the paper, whereas this one, which had equal parts, is pretty much dry already and isn't going anywhere. So, after reviewing it all, The original hypothesis was that the diamine was a very important component in the cross-linking of the epoxy. However, upon setting it up, I was really sure that the stoichiometrically approved amounts, or at least the amounts that were closer to the stoichiometric norm of a 1-to-1 ratio, was going to be the most hard set of them all, and wouldn't be able to remove that. While it definitely did set and was hard, it was not as hard as the diamine. It turns out the diamine is a lot more important than even I realized in setting up the experiment. The resin base, without the diamine hardener, is simply not simply not effective in the polymerization process, and that pretty much amounts to the conclusion. There's probably a number of things that we could do differently to change up the process. We probably could try some different testing methods as far as like testing the strength and the versatility. Maybe the metal plates weren't a flat enough surface. Maybe that's why it didn't stick properly. I don't know. Anyhow, that concludes the experiment, but it does highlight the importance of the diamine in the epoxy resin polymerization process.